So after looking at Planck and Einstein and how they looked at the quanta of light energy that we call a photon and how energy from light is able to displace electrons in the photoelectric effect, now we have the Bohr model which builds on both of these. The goal from looking at this would be to redefine that quantum of energy, explain how it relates to energy change of matter, and then look at atomic emission spectra and talk about why they occur. Here are some review questions. You're welcome to pause the video and look at them again. We talked about these in your last set of notes. So arranging colors in order of increasing wavelength, frequency, and energy. And then answering this question about yellow light, which has a longer wavelength than violet. So which one of these would be true? Whenever we look at light and the spectrum, so what we would look at as we pass something through a prism, white light is continuous spectrum from red to violet, and we see a continuous spectrum. Einstein's theory, looking at the photoelectric effect, doesn't really explain why this happens and why we see whenever we apply light energy to certain atoms, why they only emit certain wavelengths of energy. So Einstein said photoelectric effect happens if you shine a certain amount of energy from light onto a metal plate, then electrons will be emitted. But it doesn't explain why all energies of light are not emitted. Here's an example of the electromagnetic spectrum versus atomic emission spectra. So notice that the white light spectra is going to have all the colors, and the atomic emission spectra, meaning what they emit or what they give off, is going to just have specific lines in specific wavelengths, and they make a specific pattern. When we look at atoms, they are going to absorb light, so they'll absorb heat, light, electricity, and then they will re-emit that energy as light. They will emit very specific wavelengths based on what type of atom it is. We have absorption and emission spectra, so we looked at emission spectra earlier. The absorption spectra is just going to be the opposite. So whatever wavelength of light the atoms absorb, they will also then emit. This is going to happen because of the interaction of light with the electrons in the atom. And so whenever we have the absorption, the periods of complete darkness is going to correspond with the lines of emission, but that's going to occur due to where the electrons are and how they are able to absorb that energy. Each atom will emit a certain color. Now this isn't talking about the spectrum, but this is the color overall. So neon will be orange, mercury will be blue, hydrogen will be a pink light. But within each of those colors, if we break them apart using diffraction lenses or diffraction glasses, then we'll see very specific wavelengths of light that occur. You can watch the video that's linked here of the spectral lines. We'll also do an example in class where we'll look at a bunch of different gases and see what light they are emitting. So why does this happen? Why do they only emit light at certain points rather than being in a continuous spectra? And so Bohr sought to answer this question, and the way that he answered this was by developing the Bohr model, which we've looked at before. And so in Bohr's model, he has electrons that are at very fixed and specific distances from the nucleus. So we call that n equals 1, n equals 2, n equals 3 to show how far the electron would be from the orbital. What I'd like you to do is take a minute. You can pause the video. This link you can get from the PowerPoint or on Blackboard with the notes. But I want you to take a look at this simulation and see what you can do with it. So this simulation will allow you to move these little energy pieces and then excite the electron, see what happens to it, and then you can watch and see what energy is emitted down here in the right-hand corner. So as you add your pieces of energy, you can kind of see what happens, watch the wavelength of light, see how the electron responds to these different pieces that you put on. and just note the changes, note what kind of energy is released, note in general just what's happening. So after you've experimented with a few different scenarios and written down your results, compare them, think about how does this demonstrate the idea of a quanta, and how does it also support Bohr's model of the atom where there's very specific energy levels for the electrons. And then what's the electromagnetic spectrum, what are absorption and emission spectra, and how will they be the same or different for a certain atom? When we look at the Bohr model, we start to talk a little bit about quantum numbers, and this is looking at the energy for each Bohr orbit. And so we would say that it is quantized, meaning that it's at very specific levels. So the jump here between n equals 1 and n equals 2 is rather large, maybe a little smaller to 3, a little less to 4, and then so forth. So energy increases with the increasing valence value of n. So the higher n, the more energy is required to get an electron to that level. As the levels increase, then the levels are more closely spaced together. The important thing to look at, and what you hopefully saw in the simulation as well, is that electrons can't exist except at very specific levels. So an electron can't exist halfway between n1 and n2. It can only exist at either n1 or n2. As Bohr was looking at the different spectra, the different emission spectra and studying, he was studying hydrogen, and he found that with the electrons, that whenever they were in the lowest energy state, this was the ground state, and then whenever the electron gained energy or the atom gained energy, then the electron moved into the excited state. Bohr studied hydrogen because it had a single electron, and so he was able to study specifically what happened with that one electron each time that he would add energy to that hydrogen atom. Whenever we look at an electron, if it remains in orbit, then it doesn't absorb or emit energy. But if it absorbs energy, then it's going to jump up to a certain higher level and jump up to a new orbit. So this electron that's in n equals 1 absorbs energy, and it's going to be excited and go up to then n equals 3. So whenever it goes to n equals 3, it will stay there in the excited state, but eventually it's going to be unstable and it will come back down to its ground state where it normally is. So it will go from 3 and then return down to 1. Whenever this happens, it will release a photon of light with a specific amount of energy called a quanta or quantum of energy. The same thing will happen with this electron. So this electron was maybe originally in this n equals 3 or the third energy level. It was excited up to the fourth energy level, and it will release a certain wavelength of light whenever it returns back to its ground state. Because photon energy is related to a specific wavelength, then there's specific lines in our emission spectra that show the transition between the orbits. And so we're seeing specific wavelengths of light because each specific wavelength will have a certain amount of energy that is going to be released. With the Bohr model, it does a really nice job of predicting the hydrogen emission spectra, but it doesn't do a great job of predicting elements that have more than one electron. So, fairly useless, right? But in actuality, it tells us a really good fundamental principle about electron energy levels and that electrons can only exist in those certain levels. But we need to expand upon that model, and the way that model is expanded upon is through the quantum mechanical or the wave mechanical model. So in this model, it moves from the fixed orbits like Bohr shows to a more cloud-like model where electrons are going to exist in certain spots within the cloud. So, not like the cloud where you store all of your pictures from your phone, but the cloud model is predicting where the electrons are going to be. We can't predict or describe the exact paths, but we can say the probability of where an electron can be located. And with Bohr, he had the circular path. With the quantum mechanical, we have kind of a probability map of where the electrons will be located. And we'll take a bigger look at this and talk about how we can classify where the electrons might be found. Another interesting video, albeit a little bit old, is this NASA video that explains a little bit about how this information is used by scientists to determine the makeup of stars. So in summary, electrons are going to exist at specific quantized orbits with fixed energies and fixed distances from the nucleus. Electrons will be excited from the ground state to the excited state based on the energy that's put into the atom. Whenever the electron relaxes or returns back to its ground state, then it will emit light in the form of energy in the form of light. And whenever we look at wavelength and frequency, that will correspond to the difference in energy between two orbits. And so we can look at, with our light that is reduced or released, we can look at the correspondence between wavelength and frequency. We'll talk about this more in class, but go ahead and answer this question as well. Think about it, come up with your answer, and we can discuss any questions that you have in class.